Good day. In earlier lessons that we have in Math 146 and Math 147, you have learned three kinds of integrals in rectangular coordinates. These are single integrals over integrals, double integrals over two-dimensional regions, and triple integrals over three-dimensional regions. In this lesson, we will discuss line integrals along curves in two or three-dimensional space. Here are the objectives of this lesson. At the end of this lesson, you are expected to define the line integral of a vector field along a curve, explain the main features of determining line integral techniques, and lastly, solve line integrals by using some techniques. Let us get to know line integrals of vector fields. According to Helm 2008, line integrals was concerned with evaluating an integral over all points within a rectangle or other shape, or over a cuboid or other volume. In a related manner, an integral can take place over a line or curve running through a two-dimensional or three-dimensional region. Line integrals may involve scalar or vector fields. Those involving scalar fields are dealt with first. Line integrals in two dimensions. A line integral in two dimensions may be written as the integral of f of xy dw with respect to the given curve C. In this figure, we have here the representation of a line integral and its projection onto the xz and yz planes. So there are three main features of determining this line integral, that is the integral of f of xy dw with respect to c. So we have the first feature, which is f of xy. This is the scalar function to be integrated. For example, f of xy is equal to x squared plus 4y squared. Then we have c. C is the curve along which integration takes place. For example, y equals x squared, or x equals sine y, or x equals t minus y, and y equals t squared, where x and y are expressed in terms of a parameter t. Then we have dw. So this gives the variable of integration. Three main cases are dx, dy, and ds, as we can see in the figure. Then ds may be written as ds is equal to the square root of quantity dx squared plus the quantity dy squared, as we have known last time in the differential of the arc length, or this is the differential s. Then the fourth case is that when we have f of xy has the form f sub 1 dx plus f sub 2 dy. This is a combination of the cases dx and dy. The integral f of xy ds along the curve C represents the area beneath the surface z equals f of xy but above the curve C. A particular case of the integral f of xy ds with respect to the curve is the integral of 1 ds along the curve. This means rather of calculating the length along curve, that is an arc length. Then the integrals f of xy dx with respect to the curve and the integral of f of xy dy with respect to the curve C represent the projections of this area onto the xz and yz planes respectively, as we have seen in the figure from the previous slide. Here are the techniques for evaluating line integral. Number one, express all quantities in the integral in terms of a single variable. Number two, if the integral is with respect to x or y, then the curve c and the function f may be expressed in terms of the relevant variable. Number three, if the integral is with respect to ds, normally all quantities are expressed in terms of x. Then lastly, number four, if x and y are given in terms of a parameter t, then t is used as the variable. These are the concepts of line integrals, and let us apply them in some examples.